Welcome to the Explainer. Today, we're going to pull back the curtain on the digital world. We're going to look at the invisible blueprint that powers literally every piece of software you use, from your favorite game to the apps that run the entire global economy. So, have you ever really wondered about this? What makes one app feel totally seamless and another one just clunky and frustrating? We've all felt it, but I promise you the reason isn't magic. The secret, it all lies in their architecture. It's this powerful combination that engineers call data structures and algorithms, or DSA for short. You can think of it as the core logic, right? It dictates how efficiently a program can think and act, long before a single line of code for the cool user interface is ever written. Okay, so if we want to build fast software, where do we even start? How do you measure the speed of your code? It's really not as simple as just, grabbing a stopwatch. See, instead of timing how long a program takes on one specific computer, which can be super misleading, engineers focus on a much more fundamental question. What is the growth rate? They analyze how an algorithm's performance changes as the amount of data it has to chew on gets bigger and bigger and bigger. And this is where they use a tool called Big O notation to grade an algorithm's efficiency. Honestly, it's like a report card for your code. At the top of the class, you've got O1, or constant time. That's the gold standard. An algorithm with this grade takes the same amount of time no matter how much data you throw at it. But as you go down this list, man, things get exponentially worse, all the way down to ON factorial, which is a true computational nightmare. And the stakes here are just incredibly high. I mean, let's say you have 1 million items to process. If you choose an inefficient O of n squared approach, your computer has to perform 1 trillion operations to get the job done. 1 trillion. An efficient choice could make the task instant. A poor one can make it practically impossible to solve. So, speed is the goal. We get that. But before we can process anything, we have to get our digital materials organized. And that's where the first half of DSA, data structures, comes into play. Well, the most basic choice is often between an array and a linked list, and it's all about trade-offs. An array is kind of like a numbered shelf. You can grab any item instantly if you know its position. A linked list, on the other hand, is more like a train. It's super easy to add or remove cars, but if you want to find a specific one, you have to walk from the engine all the way down the line. Now, building on top of these basic structures, we can create more specialized tools. A stack operates on a last-in, first-out principle. Just think of the undo button in any app. The very last thing you did is always the first thing to be undone. Yep, that's a stack in action. And the total opposite is a queue, which works on a first-in, first-out basis, just like a line at a coffee shop. The first person to get in line is the first one to get served. This simple idea ensures fairness and is used absolutely everywhere, from managing your print jobs to handling requests on a web server. Okay, so our data is perfectly organized. Check. Now we need the second half of DSA, the right recipe, or algorithm, to actually do something useful with that data. Let's look at a simple task, finding one item in a list of 1 million sorted items. A linear search would check them one by one, potentially taking 1 million steps. But a smarter algorithm, binary search, just repeatedly splits the list in half. Its worst case? Just 20 steps. 20! That's not an improvement, that is a complete game changer. Sorting is another one of those fundamental tasks, and it turns out there's no single best way to do it. You might use something called merge sort when stability is absolutely critical, like making sure financial transactions stay in their original order. But you'd probably pick quicksort for its raw speed in most general cases. The right choice always depends on the specific problem you're trying to solve. So, here's the crucial point, the thing you have to remember. Data structures and algorithms are two sides of the same coin. An amazing algorithm is totally useless if the data is a mess. And a perfectly structured data set is just sitting there without a powerful algorithm to act on it. So how do developers take these fundamental building blocks and actually use them to solve brand new complex problems? Especially when the pressure's on, like during a big technical interview. Well, they don't reinvent the wheel every single time. Instead, they rely on established problem-solving patterns. You can almost think of these as cheat codes or expert-level techniques for common situations. Patterns like two-pointers or sliding window are like reusable templates that help turn a confusing new problem into a familiar, solvable one. Let's take that two-pointers technique. Imagine you have a sorted list of numbers, and you need to find 2 that add up to a specific target. Instead of checking every single possible pair, the slow way, you can start 1 pointer at the beginning and 1 at the end, and just move them inwards. It's incredibly efficient and avoids that slower brute force approach.
But here's the deal. Learning these concepts isn't a one-and-done task. It's a craft. It's a skill that is constantly being honed by a vibrant and global community of developers.
And for a powerful example of this craft in action, let's look at Nairobi, Kenya. This city has just rapidly emerged as a major global tech hub, and that growth is being driven by a deep community focus on mastering these foundational computer science skills. It all starts with a strong academic foundation. You've got institutions like the University of Nairobi and JKUAT creating a pipeline of world-class engineering talent, all grounded in a rigorous, deep understanding of data structures and algorithms. But the learning gets supercharged by what happens outside the classroom. Professional meetups, competitive coding events like Nights of Code, and specialized groups for AI practitioners, they all create this rich ecosystem where knowledge is shared and skills are sharpened against real-world challenges. So when you boil it all down, here's the key takeaway. Whether you're in Silicon Valley or Nairobi, DSA is the shared language of efficient software. It's what separates the fast, seamless apps from the slow, frustrating ones. And understanding these tools isn't just about passing an interview. It's about having the power to build technology that is fast, scalable, and truly resilient. This is the invisible architecture that runs our entire world. Once you master it, the only question left is, what will you choose to build?